Everyone, so we're going to continue our discussion with energy, and we're going to talk about the next type, which is potential and kinetic energy. For the most part, we're just going to briefly go through them. Now, these are both very common types of energy, so you're going to be using them a lot, even though we are breezing through it. The only reason I'm doing that is because we're going to be constantly referring back to it, so you're going to get a lot of practice with it. So I mentioned this before when I talked about energy originally in the first video, that potential energy is essentially, as the name implies, energy that has not that is stored that has not yet been converted into some other type of energy. Typically kinetic, but it could go into any of the other types like work or even a different type of potential. So that's kind of what the idea. Again, like if you take an object, you lift it up into the air, it's going to have gravitational potential energy. You let go of that book, that object, and it starts to move. So it ends up turning that potential into kinetic. Um, when you eat food and you get energy from the food, what you're doing is you're getting energy from the chemical bonds that are actually storing the potential energy. Batteries, when they charge up an object and run objects after you plug them in, they have stored potential energy in the form of electrical potential. So there's a bunch of different types of potentials. We're going to start with the first one, the most common one, which is the gravitational potential. And we're going to end up talking a little bit later in this same unit about spring potential energy. But gravitational potential energy is represented by U sub G, U standing for potential energy, and G for gravitational. Now, this is something that any object that is at some height is going to experience. So, if you are at a height, you have gravitational potential energy. And one of the important things is that the greater the height, the greater the amount of potential energy you get. Again, this kind of makes sense if we think about it. You know, you put your foot underneath a book. If you drop it from a low height, like the top of a table, it doesn't hurt too much. But if you dropped it from the top of the room, it hurts a lot more. Jumping out of the first story window doesn't hurt as much as jumping out of a third story window, because in the third story window, you have a lot more potential energy that can be turned into kinetic by the time you hit the ground. Now, this actually leads into a very important question. Since potential energy depends on height, the question is, what is the height of this block? You can answer a bunch of different ways. You can talk about the height relative to the table or the height relative to the floor. And if I add in some other like pit next to it, what is the height there? So for the most part, this idea about height is actually very relative when we talk about potential energy. Because of this, whenever we talk about potential energy, what we're really going to be doing is picking 2 points, and we're going to be comparing the potentials between them and find the change of potential energy. Because if we took the potential between the book and the table, well, that kind of ignores any case that might happen where the book falls off the table, because it is still above the floor, and then the floor might have something underneath it. So for the most part, there's no such thing as an absolute potential energy, because we can always find some place lower than what we're looking for. So what we're going to do instead is talk about changes in potential. And this is going to fit our scenarios a lot better. Typically, what we're going to do, if they don't explicitly tell us where we're supposed to take our height measurement from, my go-to phrase is to have it at the very lowest possible point in the motion. So if we go back to this scenario here, if we drop this book and it's going to land on the table, it makes a lot of sense only to think about the case where the book is at 1 meter height and that's it. That this height of the table doesn't matter, the height of this pit doesn't matter. All that matters is to the table. If we have a problem where it's going to fall onto the table but then fall off onto the floor, then again, it would make a lot more sense to talk about the height going from the floor. So it, typically it's going to be based off of the question at hand, as you'll see later on. So, besides height, what other factors could affect gravitational potential energy? Well, if we think about the idea of dropping an object, we can actually tell which objects have more energy by the time they hit based off of the sounds they make, based off of the type of collision they end up having. An object that hits the ground with very low energy, low kinetic energy, typically don't make that much noise, and they don't end up creating any vibrations. Objects with a lot of kinetic energy when they hit will make a lot more noise when they hit, and a lot more vibrations being sent out. A good way to check this out: drop a very small object, a very large object, and you'll see that one does land a lot louder than the other. So that actually tells us that one factor ends up being mass. If we drop a very heavy textbook or a very light tennis ball from the same height, one of them is going to hit the table and cause a lot more vibrations and sounds occurring from the kinetic energy, smacking the table and dissipating all around versus the tennis ball. Now, the other factor comes from the name itself, the gravitational potential energy. It makes sense that the other factor for potential energy is gravity itself. So the equation we have is actually um, delta UG equals mg delta y. Now, a few things to note. First, you're going to see me very regularly not include the delta. The delta is really there mainly to keep reminding yourself that we're talking about a difference between 2 points. That it's not just some absolute potential, but more of a difference in potential of point A and point B from where it is to where it's going to be. Uh, so you don't need to include it. It's one of those things that it's very commonly dropped. In addition, I might actually, instead of using the Y term, I might regularly use MGH. Just a habit because of the fact that I always talk about height, but the way that you're going to see it on the reference table is with the deltas. Now, really quickly, one thing I want to mention is that this equation is actually found through the definition of work. In fact, gravitational potential energy, and actually all potential energies, are really just forms of work. So, by definition, the gravitational potential energy is essentially the amount of work that has to be done against gravity. That's kind of a way that a lot of colleges kind of explain potential energy. That it's the work being done against gravity. So, what I can do is I could say that work done by gravity is the same as the gravitational potential. We already have an equation for the work done by some force. It's force times distance. Since this is the work being done by gravity, it makes sense that the force is going to also be by gravity. Just like how we said before that the work being done by the frictional force was dealt with the frictional force in the equation. From here, I know one of the equations for Fg is mg, so I can plug that in and I get that the potential energy is mg times d. Well, d is a distance, and since it's being lifted up and down, I can replace the distance with height. And there we go, we have mgh. Very simple, very straightforward derivation, nothing really crazy. But I just want to point this out that when we talk about this spring potential energy, you'll see me do this again. So I wanted to first let you know that these equations aren't coming out of nowhere. It's not like some person just up and said, "Okay, I'm going to define potential energy as mgh. Let's have a party." It comes from very specific equations. It comes from our definition of work and combines with Newton's laws in order to actually figure out, what the equations could be based off of the scenarios. Now, this actually leads me into a very important statement, a statement that may not make a whole lot of sense right now, but you'll see it in one of the later questions that we do. Maybe not in this video, but in one of the practice problems we do. And the statement is that objects can't have potential energy, only systems can. This is kind of a weird statement, but it basically means that if I ask you what is the total energy of this book, let's say, that's the statement. What is the total energy of a book? That statement cannot include potential energy. When you go to calculate the total energy, you look at all the energies that could be involved on that book. Potential energy cannot be considered because you only talked about the book. Since potential energy, and in particular, this is gravitational potential energy, requires gravity, gravity only exists because of the Earth. So you might see the phrase uh, book, Earth, system. This is basically telling you that you're allowed to talk about potential energy for this object. So if they ask, "Hey, what's the total energy of the book Earth system?" they're telling you that potential energy is one of the considered forms of energy that you're allowed to do it. Later on in this video, I'll kind of give a slightly different explanation to kind of explain why this is important. But it really comes from the fact that AP Physics 1 is a very tricky test with very tricky questions, and this is one of the ways that they try to trick you up. This is something that you don't normally see outside of AP Physics 1. So here's our first question. Pause the video, work itself, and we'll go over in a second. Okay, so here we see that we have this person up at some height. They want to know the gravitational potential energy of the woman Earth system. I am going to try and change some of the terminology to reflect this idea of objects can't have potential energy, but I don't always remember to put it because, like I said, it's really just an AP Physics 1 thing, not really common anywhere else. So right off the bat, we just take the equation, plug the numbers in, and we get our answer of 24,000 joules. Easy peasy lemon squeezy. Now, here's the issue. If you recall, I just said that this came from the fact that I took the work equation, substituted in the force of gravity in for the force, and I plugged in mg for the force of gravity. That's all good and dandy, except there's one big thing. That is not the only equation we have for the force of gravity. That's a very specific equation, being near the surface of the Earth. We do know that there is a more general equation for the force of gravity, and that is g m1 m2 over r squared times d. So if I take this and plug this into my force of gravity, I'm going to get a slightly different equation for the potential energy. And this would be used more for much larger distance, much more extreme distances, like between planets, between stars, things like that. One thing to note, just like we did before, we have to change d to make sense with the scenario. If you recall, r in this equation stands for the distance between centers. If I am some distance away from the Earth, it turns out that the distance I am from the object is the same as my distance from the center. So the d would actually be replaced with r. Having an r in the numerator and an r in the denominator, I can cross one of them out and end up getting this equation, g m1 m2 over r. There is actually one issue with this equation, though, before I keep going. You don't really need to know it, but I think it's nice to be able to have some understanding of what's going on. There's an issue here is that if you look at this equation, there's a direct relationship between potential energy and height. As height increases, potential energy increases. If I were to graph this, I get a linear line like this. As height goes up, potential energy goes up. If I look at this equation, though, let me rewrite it. G m1 m2 over r. If I were to graph this, potential energy versus r, which again is just another term for height, I don't get an increasing scenario. I get decreasing. Well, this doesn't make sense. These are the same. These are technically the same equation. I'm just replacing the very specific form of g with the more general form of g. G m over r. So there's no reason why the equation should somehow change as I get further away. Because if I turn this and used it over small distances by the surface, I should still get an increasing value. So because of this issue, because of this contradiction, we have to kind of correct this equation so that we end up getting an increasing form. One way to do this is to make this negative. If we do that, this line, let's see if I can actually erase, this line now gets reflected on over the x-axis, and now it looks like this. Now, because this is a negative number, now the idea of it decreasing actually turns it into an increasing term. And if we actually look at it over, the small section, we would see that it does kind of match this. So now we actually have something that makes sense with what we got in this very small window area equation. There's another reason why this equation ends up having a negative. It comes from the fact that, uh, if you recall, this is technically a change in potential energy. So what they do is they set potential energy infinitely far away minus potential energy at some point. And when it's infinitely far away, r goes to infinity, this goes to zero. So that's another reason why it ends up being negative. Like I said, you don't really need to worry too much about it. Just realize that the negative is there, it's meant to be there, and it's supposed to be there. But that's kind of where it's coming from. Okay, so why don't we do a quick practice? Pause the video, work self, and we'll go over in a second. All right, so again, we want the potential energy of the Moon Earth system. We take the equation that we have, this time with the big G because of the far distance. We plug our numbers in, and we get our answer of negative 7.63 times 10 to the 28 joules. So again, we have that negative number. Don't worry too much about it. Okay. Now, on to the last energy that I want to talk about today, and that's kinetic energy. So we talked about how kinetic energy is the energy of any object that's moving. Once again, we could think about conceptually what factors affect kinetic energy. If we considered a ball being rolled on the floor towards our foot, and we want to know what could we do to that ball to change the energy in the system. Obviously, if that ball has more kinetic energy, when it hits our foot, it's going to hurt a lot more. Well, there's two ways that I could do this. One, I can change the mass. If I roll a bowling ball and a tennis ball at my foot, the bowling ball is going to hurt a lot more than the tennis ball. The bowling ball has more mass, it has more inertia, therefore, it's going to end up having a lot more kinetic energy. Likewise, another thing that I could change is the speed. If I make the bowling ball roll, if I have two baseballs, one rolling very, very slow and one rolling really fast, the fast object is going to hurt a lot more than the slow rolling one. So the equation we have for kinetic energy is 1 half mv squared. Interestingly enough, this equation can also be derived using the work equation. So what we can do is assume the case where I'm applying work to an object in order to speed it up, and we're doing this horizontally. Once again, work is going to be equal to force times distance. Now, our very major equation for work is mass times acceleration. So I have mass times acceleration times distance. If you recall, we have an equation that has acceleration times distance. V squared equals V naught squared plus 2AD. Now you might have it written as x minus x naught, but I like to just simplify it to d because usually x naught is always dropped to 0. So we have this. If our object started at 0 and this drops out, what I can do is I could divide the 2 over, and I get AD is equal to 1 half V squared. Plug this in for AD, and I get M 1 half V squared, or K equals 1 half MV squared. So again, these equations aren't coming out of nowhere. They're not being pulled from the ether. They're being derived from a definition of work combined with the Newton's laws and the kinematics equations, things that can be easily measured. Now, if you recall, in the statement that I made about potential energy, I said that only systems can have potential energy. Here, it turns out that kinetic energy can be, I guess, had objects and systems can have kinetic energies. So if we go back to that question that I said before, there's a really common question that I've seen in the AP1 pop up a few times, where they'll have a part where it says, what is the total energy? What is total energy for a ball? And then the next question, like right after it, is basically asking the same thing. So, what is the total energy? And then it'll say for the ball or system. And what you're supposed to know as a student is that in case A, even though it seems like A and B are asking the same thing, case A is saying that the total energy is only kinetic energy because only the objects can only have kinetic energy. But in section B, since we're talking about a system, then what we can do when we do kinetic energy, the total energy, it'll be the kinetic plus gravitational potential. In fact, one thing that's really interesting is that the whatever they add to the system, each one is going to carry a different energy. So you might actually see a question that says something like the ball earth spring system. Now that seems complicated, but what that means is the ball carries the kinetic, the earth carries the potential energy, gravitational potential, spring carries the spring potential, and so on and so on. That's usually the as far as it will go, but just in case you ever see something that says some other term, that usually means is that that added object to the system is bringing in an additional energy that we weren't allowed to account for in the previous part. Like I said, you'll see a question like that later on. It really only comes up in a lot of the tests. It's not really something that I kind of stress too much, only because I kind of want to focus on having you guys be comfortable using the equations. All right, so here's the kinetic question. So pause the video, work itself, and go over in a second. All right, easy enough. We take the equation for kinetic energy, plug the numbers in, chug out an answer. We get 45 joules. Bada bing, bada boom. All right, that's it. I'm gonna leave it there. So those were the types of energies. We'll talk about power in the next video. But for the most part, you should just be able to do plug and chugs. You should be comfortable knowing how to use the equations and when to use the equations. In the next topic, not the power one, but conservation of energy, we're going to finally see how energy kind of can make this concept a little bit trickier by combining these energies together. So if you have any questions, feel free to let me know. Otherwise, good luck and have a great day.